Hello, my name is Andreas Fichtner. I'm a geophysicist at ETH Zurich. In our group, we do research on deformation sensing using fiber-optic cables, such as these ones. An emerging technology that recently caught our attention is integrated fiber-optic sensing, which is in contrast to the much more widely used distributed fiber-optic sensing, also known as DAS. The basic principle of such integrated systems is as follows. A laser signal is injected on one side of the fiber and is received after some time on the other side. Deformation of the fiber changes the time it takes for the signal to travel from one end to the other, and therefore the signal arrives with a phase change delta phi. The outstanding advantage of such integrated systems is their long interrogation distance of thousands of kilometers. The price to pay is an apparent lack of spatial resolution because the measured phase change is integrated along the fiber. These properties are orthogonal to the properties of distributed fiber-optic sensing that suffers from rather short interrogation distances, but offers high spatial resolution. Now, we were wondering if integrated systems really have no spatial resolution at all, and if so, if anything could be done about it. Key to answering this question is this equation, which states that the measured phase change is proportional to the integral over the local fiber curvature times the local deformation of the fiber. This equation has interesting implications. Since sensitivity to deformation depends on curvature, it suggests that the measurement is dominated by contributions from fiber segments with strong curvature. Now let's look at a toy example to understand what this may mean in practice. In this example, we consider a source that radiates a wave field consisting of a P and an S wave. The wave field is recorded by a fiber optic cable that is characterized by its local curvature vectors, shown as gray arrows. After about 81 seconds, the P wave reaches the nearest high curvature segment of the cable and thereby produces a strong phase change signal. After 84 seconds, it reaches the next high curvature point, which produces the next large amplitude change, and so on and so forth. At a later stage, also the S wave reaches the various high curvature points, which produces a corresponding set of optical phase change signals. In conclusion, we have seen that integrated fiber-optic sensing systems can make distributed measurements, which depend on the spatial distribution of high curvature fiber segments. The distributed information simply becomes accessible by data analysis in different time windows, because different time windows see different parts of the Earth. Potentials of this technology lie in distributed deformation sensing in remote regions, for example in the oceans. And this in turn is useful for studies of Earth structure and earthquake sources, but also for tsunami warning and nuclear monitoring. If you would like to know more details, please have a look at these 4 open access papers published earlier this year. 2 of them describe the forward and inverse modeling theory for integrated fiber-optic sensing, and 2 others show real data applications using a microwave frequency interferometry system. Thank you very much for watching.